Okay, chapter 6 is all about set theory and proofs that we can do with sets. So I know most of us are familiar with sets, so a lot of this first section, which is the definitions and then a new method of proof, the element method, a lot of these definitions you're probably going to know, you're probably going to understand, but we have to have them written out explicitly just like we did in chapter 4. So when we do our proofs, we make sure that we're satisfying the definitions precisely. So we have 4 things to do. We're going to go over the definition of subsets, and we'll play around with them a little bit. We won't just do proofs. We're going to look at the definition for set equality. We're going to look at operations on sets. And then we're going to discuss the empty set. And power sets. Okay, so subsets. So our definition for subsets is if A and B are sets, then A is a subset of B, if and only if, remember this is my shorthand for if and only if, all elements of A are in B. So in symbols, A is a subset of B, so this is our subset symbol. And this is the, just like less than or equal to, this means that A could be the same set as B. And we're going to allow A and B being the same set to be subsets of each other. So A is a subset of B if and only if for all x, if x is an element of A, then x is an element of B. So we could play around with this a little bit before we dive into some proofs. So if A is the set 1, the singleton set, and B is the set 1 and the singleton set 1. So I like this example for 2 reasons. One, playing around with subsets a little bit here, but also it shows and highlights the fact that sets are one of the more generic things in mathematics. They are just a collection of things, and in this set it's a set of sets, so it has a single element as well as having a whole set as one of its elements. So this is kind of what we want to be thinking about in terms of generalities, is that sets are very, very vague, and as you add properties to sets, that's when we get things like the real numbers are technically a set. They're a set of real numbers, and they have all the real number axioms that go along with them. And so when we're thinking about sets, we want to have that in mind, that they are very vague until we give them or assign them properties associated with them. So we're just going to ask a couple basic questions here. Is A a subset of B? And the answer here is yes. And that's because 1, which is an A, and 1 is in B. Now, is A, when we have this symbol without the equals, we are doing proper subset. So we're going to define this in a second. So is A a proper subset of B? And again, the answer is yes, because we have that singleton set that is an element of B, and the singleton set is not an element of A. And so we want to make sure that we're clear on the difference here. The singleton set 1 is A, but inside A is just the element 1, whereas B has the element 1 and the singleton set 1. So even though this is A is not an element of A, because A is the collection of things that makes up the set. Inside the collection B, we have 1 and another collection of 1 element. So let's define proper subset. And it's just highlighting what we just looked at in this example. So we say A is a proper subset of B if there is some element of B that is not in A. So in other words, there exists an X in B such that X is not in A. That's what a proper subset is. And we use the symbol, the little C thing here without the equals. So now that we have our definitions in place, let's go ahead and look at proof. So our element method is how we're going to prove most things in this chapter. So to show X is a subset of Y, an improper subset. 1, we let little x be an element of capital X, be arbitrary. And 2, we prove that X is also in capital Y. And then we can conclude that X is a subset of Y. So if you take any arbitrary element of this set, and you show that it's always going to be in this set, then you can conclude that you have a subset. So let's take a look at a little example. So we are going to prove that A is a subset of B if A equals the set M that are integers, such that M equals 6R plus 12, where R is also an integer, and B is the set of integers N such that N equals 3S, where S is also an integer. Okay. So we're going to let little a be an element of A. Then there exists an R that's an integer such that A equals 6R plus 12, right? That's just our definition of being an A. So if little a is an A, it satisfies this. We can find that integer. Well, we can factor a 3 out of this to 2R plus 4. And since 2r and 4 are all integers, follows that 2r plus 4 is an integer. So A is an element of B. Therefore, capital A is a subset of B. That's our element method. We took an arbitrary element in here. We used the definition from that set. We worked it into what the definition of the other set looks like, 3 times an integer. And so we can claim subset. So some subset proofs are harder, some are easier. It just depends on what your sets look like. So let's talk about set equality. So 2 sets, A and B, are equal if and only if A is a subset of B and B is a subset of A. So if everything in A is in B and everything in B is in A, well then they have to be equal. So this is how we're going to prove set equality, by showing that 2 sets are subsets of each other. So let's take a look at a little proof of this. Not this theorem, but using this. So we are going to prove that A, which equals a set of integers m, such that m equals 2a, where a is an integer, is equal to B, which is defined as the set of integers n, such that n equals 2b minus 2, where b is an integer. So we need to show that A is a subset of B and B is a subset of A. So we're going to start with the first one. So let M be an element of A. Then there exists an integer little a such that M equals 2A. And 2A is certainly equal to 2A plus 2 minus 2, which we can write as 2 times A plus 1 minus 2. Since A and 1 are integers, it follows that t equals a plus 1 is an integer. So m equals 2t minus 2, which is, of course, an element of B. Thus, A is a subset of B. So now we have half. So next, let n be an element of B. Then there exists an integer b, little b, such that n equals 2b minus 2, which we can write as 2 times b minus 1. And just as before, since b and 1 are integers, it follows that, let's call this r equals b minus 1, is an integer. So n equals 2 times r, which is an element of A. Thus, B is a subset of A. So, since A is a subset of B, and B is a subset of A, we conclude that the set A equals set B. And that's the end of our proof. So anytime you have to prove set equality, this is the way that you want to do it. You want to take an element of one and show that it sits in the other. So you have that subset. And then take an element of the second set and make sure that it sits in the other. And notice that each of my proofs here are completely self-contained from one another. I didn't repeat any letters. I didn't assume that this m was the m that I was trying to get down here for this 2r. We just do it isolated from one another. But it all sits in the same proof. Okay. So let's talk a little bit about set operations. So a lot of these we're going to hopefully know. Two of them for sure I know that you know. Set operations. So we're going to let A and B be subsets of a universal set U. Well, number one, we have the union of sets, A union B. This is the set of X that are elements of U, such that X is in A or X is in B. This is our union. Union, remember, is the disjunction of sets because it's an OR. Then we have the intersection, A intersect B. This is the set of X's that are in U, such that X is in A and X is in B. As I said, this is the intersection. Didn't give myself enough space there. Still didn't give myself enough space, but that's okay. That's our intersection. It's our conjunction of sets. Then we have set difference, B minus A. This is a set of X that are in U, such that X is in B and X is not in A. So the difference of sets are the things that are in the first set that are not in the other set. So this is our difference. Notice that B plus A is really just the union because it's the set that B plus A would be things in B or things in A all put together. And that's exactly what the union is. And our last operation for sets is the complement set. So A complement is the x that are in U such that x is not in A. And there's a property for complements. A union A complement equals our universal set. Everything in A plus everything that's not in A gets us back to the universal. So this is the complement. So I do have some drawings here to help you see what these are just a little bit better. So let's say we have our universal set U given by this rectangle, and we're going to do one of these for each of our set operations. So let's start with A union B. So we have A and we have B. So A union B is everything that's in both. That's the union. Stuff in A and stuff in B. Then we have, so this would be A union B. Do A intersect B. So if this is A and this is B, the intersect, as we know, is just the things that are in both. Set difference, B minus A. If we have A and we have B, the difference, B minus A, would be all the stuff that's in B that's not in A. So that would be this stuff, not including the things that overlap. And then finally, if we have A and we have B, A complement, it's everything that's not in A. So that is all of this. Including the stuff so everything not in A. So you can see that B minus A is going to be a subset of A complement, just like the intersection is a subset of the union. Okay. So let's talk a little bit about our real number sets and our set builder notation. So I've been using set builder notation this section, and you will hopefully recognize it if you haven't already. So a set of real numbers such that, you know, we can have x is less than A or x is greater than B, something like that. When we have set builder notation like this, we're implying that A and B are real numbers since our x's only come from real numbers. So we can write our unions and our intersections and all our other sets as set builder notation. So let's do a little example practicing just writing some sets. So we're going to write as a set where the universal that we're dealing with is the real numbers. And our sets A are going to be the set of real numbers x such that -1 is less than x is less than or equal to 0. And B is the set of real numbers x such that 0 is less than or equal to x is less than 1. And we're going to write A union B, A intersect B, I don't need a comma there, A complement, and B minus A. I'm just going to write this over here. All in set notation. So A union B, if we are between -1 up to 0 and between 0 up to 1, and we can be in this or this, then this is the set of real numbers x such that -1 is less than x is less than 1. Now we're not saying that every single value that's in the union, well, we are saying every single value falls in this, but they come from this interval or this interval. So if you're in this interval, you're still in this one. And if you're in this interval, you're still in this one. So this becomes our union. Our intersection, this is the set of x that are reals such that -1 is less than x is less than or equal to 0, and 0 less than or equal to x less than 1. So you're looking for the overlap, and the only overlap in these two intervals is 0. So this actually simplifies down to just the singleton set of 0. So that's our intersection. You're looking for the overlap. Excuse me. Our complement. This is everything that's not in A. So if we are using the reals as our universal, it's the set of real numbers x such that x is less than or equal to -1. And x would be greater than 0. Because we want to be bigger than this, smaller or equal to that. So that's our set for the complement. Our set difference, B minus A. This is the set of real numbers x. So these are the things that are in B, but not in A. So the only thing, if you've done your intersection first, you're basically eliminating the stuff that's in the intersection. So since we only have 0, this is 0 less than x less than 1. That's our set. So just some problems with set things in the homework. You'll have to build some sets like this. The next thing we want to talk about is collections of sets. So creating unions and intersections of collections. Unions and intersections intersection of sets. So we're going to let capital A sub 0, capital A sub 1, capital A sub 2, dot, 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 just continuing, all be subsets of a universal set U. Okay, so for n greater than or equal to 0, the union, big ol' union, from I equals 0 to n of A sub I, this is just the union of all the sets. A1, A2, union dot dot dot, union all the way to AN. And so this is nothing more than the set of x's out of our universal, such that x is in A sub I for I coming out of 0 to n. So I is our index. So our index comes from either 0 all the way up to n. It can come from any of these sets here. And if we take the infinite union from I equals 0 to infinity of A sub I, well, this is the x's that are in the universal such that x is in A sub I for some I. Now, if you take the infinite union of all subsets that you can create, sometimes this is going to equal your universal, sometimes it's not. So a lot of people right here want to say, well, isn't this just equal to U? Potentially, but we haven't said that all of our subsets span the entire amount of elements found in our universal U. So yeah, sometimes this will be your U, sometimes it won't, which is why its definition doesn't get the equals U here. So we can do similar things with intersections. So from I equals 0 to n of A sub I, this is A naught, intersect A1, intersect A2, intersect dot dot dot, all the way down to AN. And this is the set of x's out of our universal U, such that x is in A naught and x is in A1 and dot dot dot, and x is in AN. So you have to be in all the sets to be in the big intersection. And again, we can take an infinite intersection from I equals 0 to infinity of A sub I. This is the set of x's coming out of our universal U, such that x is in A sub I, and this is for all I that are greater than or equal to 0. Now, a lot of times, this infinite intersection is very small, 1, 2, sometimes no elements at all. So we can construct things like this, and you're going to have some practice in the homework building sets like this. Just know that you're going to follow these instructions. When we start looking at subsets like this, either intersecting or unioning a bunch of them, we want to have some language to talk about them a little bit more. And so that's where disjoint sets comes in. So two sets, A and B, our disjoint if and only if A intersect B is the empty set. So the empty set, you can write it like this, or you can write it like this with empty curly braces. But this means it's the set of nothing, not the set of 0, not the set of the 0 element. It's the set of nothing. There's nothing there. So if you're in the habit of writing your zeros with a slash through them, you must stop this now. You can't do it anymore, because in this chapter and moving forward, we're going to see this as the empty set. And the empty set is a very important set. It allows us to prove a lot of things because of how it works. We're going to talk more about the empty set throughout the chapter. So along with disjoint sets, we have another definition called mutually disjoint. So let's say we have sets A1, A2, A3, ... We say these are mutually disjoint. Disjoint if and only if each pair is disjoint. So what we mean by that is A sub I intersect A sub j equals the empty set whenever I does not equal j. So if you look at two unique sets, they should be disjoint. So A1 and A2, A1 and A3, A1 and A4, also A2 and A3, A2 and A4, A2 and A5. Any pair of sets needs to be disjoint for the whole of them to be mutually disjoint. And our next definition that goes along with this is about partitions. So a collection of non-empty sets, A1, A2, A3, ... all the way to AN. Is a partition of A if and only if, number one, A equals the infinite union from I equals 1 to infinity of A sub I, or, well, why don't we just do this? You can have the infinite version, and you can also have the finite version from I equals 1 to n of A sub I if you're finite. So we're going to work off the infinite version. So if you have an infinite collection, your infinite union needs to equal your big A. And if you have a finite, then your finite union has to equal A. Whichever one, whatever type of partition you're looking at, an infinite or a finite number of non-empty sets. And the second thing that also has to be true is A sub I, the set of A sub I, must be mutually disjoint. So we work with partitions all the time in the real numbers. Anytime you partition the real numbers from 0 to 1, 1 to 2, 2 to 3, so on and so forth, you're building mutually disjoint sets, because from 0 to 1 intersects with nothing from 1 to 2, as long as you don't have equality on your endpoints. But you have to have mutually disjoint sets. They're infinite union if there are infinite ones, or finite union if there are finite, have to union up to equal the big thing. And then you can say you have a mutually disjoint, or a partition of your big set A. So our second to last definition is power sets. So power sets definition is given the set A, the power set of A, which is denoted with this fun scripty P of A. So P of A is the power set. This is the set of all possible subsets. Now, this is not always easy. In fact, we're going to do a little problem here, or you're going to do a little problem here, finding a power set of a relatively small set. So in this example, I want you to find the power set of 1, 2, 3, and 4. So your items in the power set, this is a set of sets. So all of your items inside the power set require a curly brace. Now, I want you to actually work this out and try. So I'll get you started. So the power set of A, first it contains all the singleton sets. 1, 2, 3, and 4. Then it contains all the subsets that have 2 elements, and then all the subsets that have 3, and then the subset that has 4. So each of your elements in a power set needs curly braces, which is annoying, but you still have to write them. So I'm going to continue on. You should pause it here and try and write out all the subsets, and then check your work. So we have 1, 2. We have 1, 3. We have 1, 4. We have 2, 3. We have 2, 4. We have 3, 4. That ends the 2 element subsets. Then we have 1, 2, 3. 1, 2, 4. 1, 3, 4. I need more space. So 1, 2, 4, 1, 3, 4. And then it would be 2, 3, 4 would be the last 3 element, and then 1, 2, 3, 4, the improper subset. So that is the power set. So you have to get every single one all together. It's a pain, and you can see this was just for 4. Imagine you had 5 or 6 elements in your subset. Power sets become very hard to write out by hand. So our last definition is the Cartesian product of sets. So the Cartesian product for sets A1, A2, to AN, a Cartesian product is A1 cross A2 cross cross AN, which equals an ordered n tuple. So this would be A1 comma A2 comma all the way to AN, such that AI is an element of capital AI, and I in this case goes from 1 to n. So every piece of your n tuple, each component comes from the corresponding indexed set. So little a1 comes from set a1, little a2 comes from set a2, little a3 would come from set a3, all the way down to little an comes from set an. Now, we know a very famous Cartesian product. It's the real number axes. So this is a little example. R cross R is the set of ordered pairs, x comma y. So it's that x is a real number and y is a real number. And because of this, you'll often see this written as r squared. But this is a Cartesian product. It's one of the reasons we call the xy axis the Cartesian plane, because both of these constructions come from Descartes. And good old mathematicians are very, very egotistical. So let's build some Cartesian products. So we're going to let A1 equal xy. We're going to let A2 equal 1, 2, 3. We're going to let A3 equal AB. And we are going to form 3 of these. We're going to do A1 cross A2. We're going to do A1 cross A2 cross A3. And you can make some complicated Cartesian products. So we are going to cross A1 cross A2 cross A3. Now when you're doing Cartesian products, parentheses become very, very important. So try this out. Try and construct these on your own. Pause the video and do it. And I'm going to just walk through the answers here. So hopefully, if you're watching this now, you've finished at least part A. So our Cartesian product A1 cross A2 will be the set. We have x comma 1. We have x comma 2. We have x comma 3. We have y comma 1, y comma 2, y comma 3. And that's it. We have all the combinations that x and our a2 values, and then we have all the combinations of y and our a2 values. So you just take each one and you form however many sets you have, that ordered n tuple, in this case it's an ordered pair, of every combination. So for B, A1 cross A2 cross A3, we're forming ordered triples. So we can have x, 1, and A. We can have x, 1, and B. We can have x, 2, and A. We can have x, 2, and B. We can have x, 3, and A. We can have x, 3, and B. And then there's no more that we can have with x's. So we'll start with y, y1 and a, y1 and b, y1, oh, shouldn't be 1 anymore, should it? Should be 2. y2 and a, y2 and b, and then y3 and a, y3 and b. And that is our ordered triples that come from A1 cross A2 cross A3. So before we finish C, double check that you've got these answers. For C, A1 cross A2 crossed with A3. We're actually going to write this out in set notation because this one's a little bit tricky. So these are ordered pairs, UV, such that U is an element of A1 cross A2 and V is an element of A3. So this means that U is an ordered pair in and of itself. So U is all of our elements from part A. And then we take each of these and create an ordered pair with elements from A3. So our elements for this Cartesian product look weird. So we have x1, comma, A, that's one ordered pair. We have x2, comma, A. We have x3, comma, A. Then we have y1, comma, A. Then we have y2, comma, A. Then we have y3, comma, A. Now we can do all the b's. So it's x1, comma, b, x2, comma, b, x3, comma, b. Now we can do the y's, y1, comma, b, y2, comma, b, and y3, comma, b. So when you start making more exotic Cartesian products with parentheses, your sets or your elements can look weird. So these are ordered pairs of ordered pairs with one element. You can have ordered pairs of ordered pairs and ordered pairs. So we could have crossed A1 cross A2 and crossed that set with parentheses with A3 cross A1. And it would look very, very weird. So in the homework, you're going to be creating some strange Cartesian products and getting some practice with them. But this is the end of 6.1.